All right. So an isosceles triangle is a triangle with two sides that are the same measure. The same measure. That the word for that is congruent. And off to the side. So this is your own note guide. You're going to keep this note guide. You're not turning this into. This is for you. Let me draw an isosceles triangle. Two sides are the same. Look at that's isosceles. That's an example one. Draw that one with me. A triangle with two sides that are the same measure. A triangle with two sides that are the same measure. How about this? Draw another one with me, but make this one a right triangle that's isosceles. Look at this. Here's a right triangle. We're familiar with that. But what if these two sides were the same? That would be a right isosceles triangle I just drew, and you're going to draw also. Second word. Triangle sum theorem. You're going to write this one in. The first one was written for you. Underneath the isosceles triangle, let's just go ahead and write triangle sum theorem for me. The interior angles of any triangle added to be 180 degrees. Some of my veteran students in here will recognize this one. So this is the second theorem I'm throwing at you this summer. The first was a Pythagorean theorem. Now it's called the triangle sum theorem. Here's our second theorem. Remember, a theorem is just a fancy word for a what? What's a theorem? A law. It's a law of mathematics. It's always true. So here's a law. I'm laying down the law on you guys. The interior angles of any triangle added to be 180 degrees. Let me explain. I'm going to draw a picture of the situation here. Go ahead and draw a right triangle. Let's say this angle is 50 degrees. That's an interior angle. And let's say this angle is x degrees. That's an interior angle. We can solve for x here using this theorem. This theorem goes for any triangle you'll ever come across for the rest of your entire life. If you have a triangle, no matter if it's a right triangle or any type of triangle, you know that all the angles inside the interior, they have to be 180 degrees. So knowing that, we can solve for x here. How many degrees is this? How many degrees is that angle? 90. We got 50. We got x. So look at how I'm going to use this theorem to solve for x. X plus 50 plus 90 equals 180. I know that's the case just by this theorem. Now I can solve for x. Watch. All right, so it'd be 140 equals 180 plus x. Let's subtract 140 from both sides to get x by itself, right? So x will be 40 degrees. That's what this angle would be, 40 degrees. So far, so good. Now, before we end our notes, let me just set something up now. Any questions on that? Those first two words. Isosceles, that's two sides congruent. Triangle sum theorem. All the angles inside a triangle have to be 180 all the time. So if you know two angles, you can solve for the third. Anytime. Now, what I'm going to do. let's look at all the right triangles I'm going to draw randomly. Just a bunch of right triangles everywhere. We do a different kind here. Watch this. Okay, they're all right triangles that I just drew. Don't draw these, just pay attention really quick here. Look at small ones, big ones, medium-sized ones, they're all right triangles. Okay, now, let's say this angle was 50 degrees. That means this is going to be 40 because they all add up to be 180. If this angle was 30 degrees, this one has to be 60 because all of them add up to be 180. If this angle was 70 degrees, this angle has to be 20 degrees because all three of these add up to be 180. So there's different kinds of right triangles I threw at you here. What we're going to cover now is a very special kind of right triangle. Not just any willy-nilly right triangle, like I randomly threw up here. A very special kind of right triangle called, watch this, called a 45, 45, 90 right triangle, where these two angles are 45 degrees and this one's 90. This right triangle has a lot of special features, special characteristics, special properties that help us in real life situations. That's what we're going to cover right now. And there's actually a theorem named after that kind of triangle, which is on your paper, and that theorem is called the 45, 45, 90 triangle theorem. Here we are. You have your paper in front of you. This is all on your paper. Look at what this law says. Scale, they're almost done. Look what this law says. This law says, look, if you have a 45, 45, 90 right triangle, underline this with me on your paper. The hypotenuse is radical 2 times as long as each leg. Radical 2 times as long as each leg. It's right in front of you, right? So I want you to underline that part on your paper. What symbol do we use for the word is in math? What symbol do we use for the word is? Equal. So hypotenuse equal rad 2 times the leg. Look at, so what I want you to do in your notes now is where you underline, put an arrow, and look at, there's the equation right there. Put an arrow to that equation. Hypotenuse equals leg times the square root of 2. Now on the picture on your note guide here, this picture, I want you to put an arrow at the both legs here like this. Put both legs are always the same. If you have a 45, 45, 90 right triangle, the legs will always be the same size. It'll be isosceles. Okay? An isosceles right triangle, is a 45, 45, 90 right triangle. These are very special kinds of right triangles. Let me explain. This will always be the case. So, on this note section, I'm going to do one example here, and you're going to copy it down. I'm going to use this theorem, this 45, 45, 90 theorem, to solve one problem. You're going to copy it down. Here we go. Here's where I want you to put on that first note area. Find it. Here we are. All right, solve for x and copy this down. In your notes section there. This is notes. So So this goes in the notes section. I'm going to copy that down. All right. Here's my question. Is this right triangle a 45, 45, 90 right triangle? Argument. Well, how do you know, Valdieta, how do you know this is 45 degrees, that one? What would be your argument? Okay. So these both have to equal 90? How come? To make the 90 degrees here? Okay. You're right. This is a 45, 45, 90 degree angle, or right triangle, but your reasons are not sound. These two? But my question is, how do you know they're congruent, these two angles? The three angles are the same? These two are the same? So the sides are the same, the angle's got to be the same? I'm just asking. Okay. Let's go Horton and then Gomez. How do I know that's 45 degrees? Oh wait, she had it, that's right. My bad. She was before you. Get it. How do I know that's 45? Okay, that's the legs, but how do I know that both angles are the same? Okay, so we know, well, you know what? That's actually a legitimate reason, Ronald. That's one argument. The legs are the same, which is kind of what you said. So Valtieri, you were right. If I know the legs are the same, then I know it's 45, 45, 90. What would be another argument? Gomez, do you have another argument? Right, so he's using the triangle subtheorem. The first term I threw at you today. You just wrote it down. This has to be 45 degrees because all three have to add up to be 180. So if you take 180 minus this and minus this, you're going to have 45. That's the second argument. So there's two arguments for why we know that's 45 degrees. One is because the legs are the same. The other is your argument, triangle sum theorem. All right, now, we need to solve for x. What side is x here? Hypotenuse. So we can actually use Pythagorean theorem. But we're not going to use Pythagorean theorem. A squared plus b squared equals c. We're not going to do that. We're going to use the 45, 45, 90 right triangle theorem because it's quicker. It's actually quicker. Watch. The theorem says this. Write it down with me. Hypotenuse, I'll abbreviate, equals to the leg times rad 2, right? That's what the theorem says. Remember, we drew an arrow at that equation. Write that down with me. It's there already. Let's write it down again though. It's right there. You're done already, huh? Let's substitute. What is my hypotenuse here? Thank you. Look at it. Underneath hypotenuse, I'll put x equals. Let's follow the formula. What side is my leg? Thank you. 3 rad 2. Done. Solve for x. Oh, it was fast. X is by itself. We're done. Question. Never. If it's 45, 45 negative. Never. That's why a little while ago I put, you wrote it down with me, the legs are always the same on your notes there, right? Okay? They have to be the same. That's the theorem. That's the law. That's the law. If you have a 45, 45, 90, the hypotenuse is always going to equal to the leg times the square root of 2. It's the law. It's just the nature of reality. It's the way God created the universe. Some philosophers will argue. Not by accident. That's just the way it is. Right? Now, go ahead and flip your page. Flip your page to this right here. On the top, you have 4 exercises. We're going to go through those like in 1 minute. This is so easy, you're going to flip out. Here we go. Here we are. So you have this. Flip to this page. Let's do number 1 together. Is number 1 a 45, 45, 90? Argument. Almost. Argument. Right, so this has to be 45 since all 3 add up to be 180. This has to be 45 degrees. All right, so right underneath, let me write down the theorem. Write it down with me. Hypotenuse, to get my chicken scratch, equals leg times rad 2. What is my hypotenuse here? Number 1. One more time. N is my hypotenuse? X, huh? X is, here we go. I'm replacing the hypotenuse with X. My leg, 10, rad 2, we're done. Is that easy or what? I literally took less than 10 seconds to do that problem. It's crazy, yeah? We're solving for X. We're solving for X using the theorem. Now, we could solve for X using Pythagorean theorem. A squared plus B squared equals C squared. It'll still work. It just takes longer to get to this answer. It will still work. But this theorem is just quicker. And it's only for 45, 45, 90 right triangles. Only for 45, 45, 90s. Well, are you with me, right? Is number 2 a 45, 45, 90? Somebody says Ramos. Salazar, is it 45, 45, 90? Argument, please. Well, it has an egg. That means that just makes it a right triangle. But I'm asking, is that a 45, 45, 90 right triangle? A special kind. Okay, important. Help her out. What's the argument? Legs are the same. That gives it away. There's your argument. The legs are the same. It's 45, 45, 90. Let me write down our theorem. Write it with me. Hypotenuse equals leg times rad 2. Let's plug and chug. We're in business. Hypotenuse here is what? X, so I replace hypotenuse with X, equals leg is rad 2 over 2. We don't have to get scared. We know how to deal with radicals. Times, look at radical 2, right? How can I make radical 2 as a fraction? Nice. Fraction times a fraction. Let's not get all scared. You can handle this. You're in my class. You can handle this. Fraction times a fraction is numerator times numerator, denominator times denominator. Let's do it. What's the square root of 2 times square root of 2? Square root of 4, huh? Watch. Square root of 4 over 2. Is that rational or irrational in the numerator? Is that a rational number? Sure is. Let's simplify it then. What's the square root of 4, Ramos? 2. Okay, so it's 2 over 2, huh? What's 2 divided by 2? Beautiful. X is 1. Okay. Moving right along. Questions so far? Let's do 3 and 4. We're done for the day. No doubt. So your question, the legs being rad 2 over 2. Well, that's an irrational number over a rational number. That doesn't mean it's 1, huh? Right. So that's not 1. That's a square root of 2 over normal 2. That's different than 2 over 2. See that? That makes sense? Okay. Let's do number 3. Any questions? All right. Number 3. Is that 45, 45, 95? Yeah.
Oh, yeah.
Argument. Beautiful. Legs are the same. 45, 45, 90. I'm going to write it down. Write it with me. Hypotenuse is leg times rad 2. Important. What's my hypotenuse here? Let's do it. So I'm going to replace hypotenuse now with 8 rad 2 equals my leg is x in this case times rad 2. Let's get x by itself. What do I do to both sides? You get x alone. Subtract what? Square root of 2. But this means x times the square root of 2, so what's the opposite of times? Divide. So I'll divide both sides by radical 2. Look at what happens, you guys. If we're not an equal sign. Radical 2 divided by radical 2 is just 1. It's gone. So 1 times x is just x. 1x. Radical 2 divided by radical 2, so we just have 8, huh? X equals 8, we're done. X is 8. Thank you, Gomez. Well, I replaced leg with x, huh? That's what the leg was, it's x. So in other words, the unknown in this example 3, the unknown was a leg. Example 1 and 2, the unknown was a hypotenuse. Now look at, see the unknown, the variable? Okay.
Like that, you're supposed to do what?
By rad 2, huh? To get, because remember when we have a variable, we want to get it by itself. See, it's by itself equals 8. Because once it's by itself, that's when we know what it is. By logic. Last but definitely not least, put your seatbelt on for this one. It's gonna be all right though. And we're done for the day. I'll use red now. 45, 45, 90. I know this has to be 45 because all three have to add up to be 180. 180 minus these two will give us 45. All right, let's write out the formula now. Hypotenuse is equal to leg times rad 2. Ramos, what's my hypotenuse? 12. Here we go. So I'm replacing the hypotenuse with 12 equals leg. What's my leg? Anybody? Gracias. Divided or times rad 2. All right. Let's get x alone. Questions how? By? Square root of 2. Square root of 2 is different than 2. Square root of 2 is an irrational number. So I'm going to divide by an irrational number on both sides. Look what I get. X is alone. Yay, we're done. 12 over rad 2. We're technically done, but there's a big but now. You cannot have an irrational number as your denominator. That's mathematical bad manners. Even though we're done technically, that's 12 divided by rad 2. That's the solution. X equals 12 over rad 2. It's bad manners to leave the denominator as an irrational number. So we have to do something. That's why I say the best for last. It's real easy. Kind of like that, watch. But let me get Gomez's question before I get into that. You had a question?
No, I thought you could just divide the 12 by 2, but 11 is not 10.
Right, because that's not 2, huh? That's an infinite decimal.
Yeah.
That's 1.7 blah blah blah. No, it goes on forever. So 12 divided by 1 point blah 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 is going to be some funky number. So, but we'll have to approximate. I don't want to approximate. I want an exact answer. So here's what we're going to do. That's an irrational denominator. So what we're going to do is a process that even calculus students do sometimes. It's called, underneath you're going to put a little cloud, rationalizing I want to make the denominator rational. So I'm going to rationalize it. It's called rationalizing the denominator. Write that down. It's a one-step process, very easy. It sounds scarier than it actually is. Rationalizing the denominator, that sounds like nightmare process or something. Put a little cloud. Rationalizing the denominator. So let me take this value, 12 over rad 2, and let me tweak this. Let me fix this. Because it's bad manners mathematically to leave your answer with an irrational denominator. So here's what we're going to do. If you multiply a number times 1, what do you always get? The same number, right? Any number times 1 is the same number. Same thing with a fraction. If I take a fraction multiplied by 1, I still get the same fraction. But I can manipulate the fraction into a different looking fraction, even though it's the same, by multiplying by 1 in the form of something. So in other words, I can write the number 1 as 1 over 1. I can also write the number 1 as 2 over 2. I can write the number 1 as 50,000 over 50,000. See, I can write the number 1 in an infinite amount of ways. So what I'm going to do is I'm going to take this nasty, bad manners fraction with the irrational denominator, and I'm going to multiply it by 1. Look at, watch this. In the form of, look how I'm going to write the number 1. Radical 2 over radical 2. That's the number 1. I'm going to take a fraction, multiply it by 1, and it's going to be equal to the same fraction, because anything times 1 is itself. But the fraction, the new fraction, will be just a little bit tweaked and different. It'll look different, but it's still going to be the same value as this. And it won't have an irrational denominator. Watch. So here's a fraction times 1. That's the number 1, because anything with a numerator and denominator, that's the same as 1. So fraction times 1 is going to be the same fraction. Watch what happens. Numerator times numerator, so 12 times rad 2 is just 12 rad 2. You can't multiply a rational number times irrational. You just clump them together. Over, what's the square root of 2 times square root of 2? One more time. Square root of 4. Let's keep going. So let's take this now. Let me bring it down here so I have some room. I have 12 rad 2 over the square root of 4. Is the square root of 4 rational or irrational? It's rational. So I can write my final answer. Look at 12 over rad 2, there's my numerator, over 2. I rationalize the denominator. We can still simplify though. Look at 12 divided by 2. Exactly. So this is really 6 rad 2 over 1. But it's mathematical bad manners to leave a 1 as the denominator. Right? It's not professional. I wear a tie. I'm a professional, so are you. So we don't need to put a 1 as a denominator. We're just going to write as 6 rad 2. Done.
That's X.
That's X. So look at what we did real quick before I answer that question. I took the irrational denominator, multiplied the fraction by 1 in the form of that radical, and I was able to rationalize the denominator. Look at the denominator is now a rational number. I'm going to give you more time to practice tomorrow. Going to finish up any last loose ends on your assignment for about 4 minutes, and then get your stamp sheet out. Now, if the other has a question, hit it.
No, you use the radical 2, right, as 1.
Wait, no, I multiplied, huh? That's multiplied. Because remember, anything times 1 is itself, huh? So this fraction times 1, look, it's the same fraction, just in a different form.
Use the radical 4 and 4.
Sure, but you would get a, look at, you'd get this. Hold on.